Hi, this is David Vai with Cadence Design Systems, and this year we are a platinum sponsor to this virtual IEEE Radio and Wireless Week. So I'd like to thank you for joining me online for this brief overview of Cadence's RF and microwave design solutions.
Leading technology companies require end-to-end solutions integrated across chips, IP, packages, and PCB-based systems to meet performance, size, and cost requirements. Therefore, Cadence is evolving its design solutions to address these challenges, implementing an intelligent system design strategy for delivering world-class computational software capabilities across all aspects of electronic system design. So this has been a very busy year for Cadence as we focused on the integration of Integran EMX with the Cadence Virtuoso platform, Sigrity Clarity, which is our full wave 3D EM solver for very large problems, and the acquisition of AWR Solutions, all combining for a superior electromagnetic sign-off solution. As I mentioned, AWR, which is a leading provider of RF and microwave circuit design software, was acquired by Cadence at the start of this year, expanding Cadence's RF and microwave solutions beyond the RFIC focus of Virtuoso to offer a leading design tool for the development of compound semiconductor MMICs and RF PCB systems. So the Cadence AWR design platform integrates three main products. They are a visual system simulator for system design, behavioral level modeling of RF front ends. At the transistor and transmission line level, we have Microwave Office for circuit design with of linear and non-linear circuits and optimization based on our harmonic balance engine. And for EM extraction, we have integrated the Axiom 3D planar EM analysis along with our Analyst 3D FEM tool, which is now joined by our Clarity FEM tool. So take a look at the landscape of Cadence's RF to baseband IC and PCB system design solutions across technologies, with our platform supporting advanced design entry and management, circuit and behavioral radar and communication simulations offered through a combination of AWR products as well as Virtuoso and Allegro, integrated with our EM and thermal analysis by way of Clarity 3D FEM, Cadence EMX for IC solutions, and Celsius for thermal. Together, all these products, these platforms serve product development from concept to sign-off across all chip, package, and board technologies. And so I'd like to invite people who are not so familiar with AWR's product to our AWR, our Cadence AWR microsite to learn more, or visit our YouTube for our What's New for PA Design playlist. We have a number of short features highlighting capabilities that were just recently added this past spring to AWR version 15. And furthermore, we will be proudly sponsoring the 2020 Power Amplifier Design Forum, which will be hosted by Microwave Journal. Unfortunately, it's happening at the same time as this conference, but it will be on demand. So you'll be able to check out these various talks by key industry leaders, deep experience in power amplifier design, in particular 3.5 GaN and GaAs technologies. I've created an excerpt of our talk from on loop gain envelope stability analysis for MMIC power amplifiers. It's will be presented by Dr. Mike Roberg, who is a MMIC design fellow at Corvo, and it will be one of the talks of the PA Design Forum on November 17th. So coming up right now will be a short excerpt from that talk.
Oftentimes designers want to do things very quickly in the design synthesis phase, and ideally they'd like to integrate the stability metric into their optimization goals for the amplifier which they're designing. One interesting analysis technique that does exist and has been around for a while is the stability envelope technique, and that quickly evaluates the envelope of the normalized determinant function, but unfortunately that still fails to provide a stability margin metric, which is very useful to a designer, and also Another thing about NDF is it fails to really tell you where your instability exists. It just tells you that your amplifier is unstable, but it doesn't necessarily tell you where to look, where loop gain focuses on a specific device at a time and can tell you that information pretty quickly. So to start out with, obviously I'm designing things with field effect transistors, so obviously FET models and 3.5 technologies, and so this is a standard linear FET model, which is often used. It's a gate and a drain and a source, and there's a voltage controlled current source in there. And so in order to use this for loop gain evaluation, we need to basically break the loop of this device at the current source. And so in order to evaluate the loop gain, we evaluate the voltage gain from port 1 to port 2, and that's the loop gain. And so typically what you would do to perform loop gain analysis itself is obviously that loop gain FET model is embedded in the full power amplifier, and in this case I'm showing at the bottom a 3-stage power amplifier. And in order to analyze the loop gain, you need to basically look at each individual device, but I'm showing it at the moment for a singular device, which is Q1, the first stage device. And so what you would do is you would look at the loop gain of that particular device at a particular frequency with the RF input and RF output terminations swept around a full phase range of the Smith chart. Usually we use a 0.99 gamma. Basically you evaluate that loop gain with all of those RF input and RF output terminations, and you look at all that information and determine if your device is stable. So this kind of shows what that would look like. So at a specific frequency for a fixed RF input termination and a varying RF output termination phase, the loop gain would actually trace a circle in the complex plane. And so if you were to then go and redo that analysis for a different fixed RF in termination and sweeping the RF output termination phase, that results in a different circle. And so what you would have is for every single frequency you want to do this analysis at, you'd have this collection of circles within the complex plane, and you would look at those complex circles to determine if you're stable or not. I've shown here on this slide, there's a red dot at the magnitude 10 phase point. If you happen to encircle that point with one of these loop gain circles, you would be fully unstable. The designers that are looking at these things, we don't care about the particular circles themselves. What we really care about is the envelope of those circles, because that's what defines the worst case scenario. That defines the minimum amount of phase margin, so the most likely point at which instability would occur. And so what we really care about is the envelope. We want to understand that envelope, and if we could directly extract that envelope, it would be highly desirable, because we don't really care about what's going on in the middle. I should point out at this point that the phase margin is the thing that we typically care about the most, and that's an indication of stability margin based on many years of control theory development. And we find that often 30 degrees of phase margin is acceptable for a individual device under the conditions that we're looking at it with these high magnitude gamma terminations, as well as we're looking over device model variations in terms of capacitances and GM. So if we can get 30 degrees of phase margin with certain parameterized variations, then we pretty much know we're going to be stable in the end. If we were to have that envelope, we can directly extract the phase margin from it, whereas if we had to do that from each individual circle, that would take forever. And as we previously mentioned, there's that stability envelope technique that evaluates the envelope of the NDF. Well, we can actually use the solution to the NDF stability envelope, that mathematical solution method, that can be applied to loop gain to calculate the loop gain envelope. So therefore, the loop gain envelope at a particular frequency can be solved mathematically by analytically evaluating the phase of, say, the output termination for each phase of the input termination that results in a point on the envelope of all possible loop gains. And so that's very attractive, because now we have a direct way of evaluating the envelope of the loop gain rather than evaluating all the circles and post-processing on that. And so the very nice thing about that is it effectively converts a n-squared type evaluation problem to an n evaluation problem. And so it obviously very much increases the speed of analysis. Furthermore, all of that analysis is fully automated in Microwave Office. So to walk through this, I want to just show you a multi-stage Mimic PA example. This is just an example of a very simple three-stage power amplifier, single devices within each stage, single gate and single drain voltages. The devices are denoted as Q1, Q2, and Q3. And this is the typical analysis schematic that I would have had to apply to implement the loop gain envelope analysis method prior to having AWR fully implemented. So basically you just have your full analysis schematic. You have ports 1 and 2 defined as those basically loop gain analysis ports on Q1, the first device in the amplifier, and then ports 3 and 4 would be defined as the RF in and RF output ports, and you would extract the S parameters of the schematic, and then within output equations you would implement all the loop gain envelope equations, which I've detailed in the paper and the references. Unfortunately, obviously that would require you to use output equations, and it doesn't give you quite as much flexibility. You kind of want to have multiple different schematics to analyze different devices, and while it still is very, very fast relative to loop gain, it does require the user to do a little bit more effort than you'd really want. So the good news is AWR has taken this method and ran with it, and they have fully integrated into the software, and so they've made it very, very simple. So here's the analysis schematic you would use in AWR to analyze this three-stage power amplifier in order to evaluate the loop gain envelope, and it's very obvious that it's basically just the schematic of the power amplifier. So you just have an RF input and an RF output port, and you have embedded linear device models, and so you don't need to do any of that loop gain FET work anymore because Microwave Office will completely do it for you. So you can also evaluate the phase margin now directly within Microwave Office using a measurement, and that's it's basically just using the envelope and then pulling the phase margin from that at each particular frequency. And so now the nice thing for the designer is you can plot the phase margin versus frequency of a particular device, and so that's a highly useful thing that designers can use to evaluate stability, as well as put optimization goals around, because now you can, since this is so fast, you can integrate the stability analysis into your optimization loops, which is very, very nice. And so for this case, I've analyzed the phase margin versus frequency, and I'm showing that at 38.2 gigahertz, we have a minimum phase margin in this analysis case of 136.53 degrees. It's also important to note that AWR has a gain margin measurement if you're interested in measuring gain margin. So this is the reason, or this is the slide that really shows you why you want to do this, not just because you can measure phase margin now, which is a useful thing, but this is why you would want to use this method rather than loop gain. So just a single device embedded in this multi-stage Mimic PA analyzed from 0.1 to 50 gigahertz and 0.1 gigahertz steps with 100 phase points. Traditional loop gain would have taken about 208 seconds based on my benchmarking on my machine, whereas the AWR loop gain envelope implementation takes about 0.7 seconds to complete. So it's obviously extremely fast compared to traditional loop gain analysis. Increasing the number of phase points to 1,000 points for the loop gain envelope method only increased the analysis time to 1.28 seconds. So it's very, very, very fast. Analyzing all three devices with 1,000 phase points with the loop gain envelope method in AWR only took 3.11 seconds. The traditional method, I didn't even try to run that with 1,000 phase points because it would have just probably crashed or taken hours. The traditional method, though, using the 100 phase points would have taken well over 600 seconds, obviously. And so it's unbelievably fast relative to the traditional analysis, and it also gives you the phase margin directly, whereas traditional analysis designers would typically plot all the rat's nest of loop gain circles on one plot and just find the worst case from looking at it and be done with it. But that obviously is not a method that you can directly integrate into an optimization loop to optimize the stability of your amplifier.
So that was just a short excerpt of the presentation given by Dr. Michael Roberg at our PA Design Forum that was hosted by Microwave Journal. The full version of loop gain envelope stability analysis for Mimic power amplifiers, along with the other presentations, is available on the awr.com website for free viewing on demand, as well as other information with regards to AWR products. And I'd like to thank you for your time and enjoy the IEEE Radio Wireless Week.